Okay, so I think maybe we should get started. Before we start, any questions so far? If it is quick, then I can address it now. Otherwise, we'll do it at the end of the class. Okay, so very well. We spent quite some time defining metric spaces and importantly, topology on the metric spaces. So we saw open sets. So open sets are just unions of open balls, right? And then we saw this very small but crucial observation that in an open set, I can put a ball around, an open set is not just an arbitrary union of balls, but I can take every point in that open set and put a small ball centered at that point, which is all contained in that open set. Okay. Yeah, and we saw this definition of continuity. We said some things about continuity at the end of last class, and then I asked you to prove some results. Okay.
Sir?
Yes.
So you are not recording?
Yeah, sorry, I will.
Okay.
I'll start. But so those questions, I don't know if you tried them. If you have not, you should really try those questions. And in view of what we do in today's class, you should be able to do those questions, right? Okay, anyway, but let's go back to non-linear spaces.
Recording in progress.
Okay, so the reason why we introduced all this terminology of metric spaces and topology is that we really want to do calculus in multiple dimensions in Rn and also a little bit in complex finite dimensional complex vector spaces. So I will not define a non-linear space once again. But let us just recall our sort of main examples. So let us say that if I have x, which is x1 up to xn, and each xi is just a real number, sometimes a complex number, then what did we do? We defined P norm. So what was the definition? I took the absolute values of each one of these scalars, which is always a real number, remember? Non-negative real number, even if xi is complex. And then what do? I take the pth power of all of these, then I sum over i's, and then finally what do?
1 by pth power of the whole thing.
1 by pth power of the whole thing. And what values can p take over here? P is a real number, can be 1 or anything bigger. All right. So again, let's just remember. And okay, finally, also, this was defined to be just the maximum of the coordinates, maximum of the absolute values of the coordinates. So let's just write down 1. Oops. So what did we see? We actually proved that we saw for which values of p did we actually prove that this is a norm?
1, 2, and infinity.
1, 2, and infinity. Okay, so and if you want in Rn, yeah, that's terrible. So and we will get to this at some point, but you will see that this is not really that important. Just in a bit. Okay, so let's write down again these pictures that we saw. And let's just do this in R2 with respect to the three norms. So if I take this maximum norm, then what is the ball of a certain radius around any point, but we might as well take the origin or any point really, doesn't really matter. So what is the ball here? Come on, this is all reduced, so we should be able to do this quickly.
And this is an axis-aligned square.
Sorry, say that again, please. So
This is yeah. So it was a square with sides.
right, exactly. So then with respect to that and with respect to, so this just means that if I'm centered at a certain point, then what this is saying is that both in the horizontal and vertical direction, so the maximum of these has to be less than some fixed radius r, and that means that if that whatever you are allowed to go maximum a certain distance in both the x as well as y direction. So if you do that, you just get a square. Now, and in case of the two norm, we just get the usual Euclidean circle. Okay, what happens in case p is 1? In this case, the distance, the absolute value of x coordinate as well as y coordinate, they have to add to less than 1. That just means that if you go in each one of the quadrants, then you are going to get in the first quadrant, you're just going to get the line x plus y equal to 1, and you have to be closer to the origin than that. And likewise, you get in all four quadrants. So what are the shapes here? So in the first case, I get squares, that is interiors of squares. In the last case, I guess interior of circles. And in here, I get interiors of diamonds. Okay. Actually, this is badly drawn, because if I turn 45 degrees, then this diamond is also going to be a square, right? All right. And so sort of a crucial thing was that inside each square, I can fit a diamond and vice versa. And likewise for circles also, right? So let's just see this. Observe. This observation has a very nice consequence in terms of topology. Remember that every norm will define a distance. And therefore, R2, or in general, Rn, is becoming a metric space in many different ways, depending on the norm that I choose. But the observation is that all of these norms will give the exact same topology. So let us see. Observe a set in R2 is open with respect to, let's go in order. So let's give a name to this set. A set V in R2 if and only if what happens? So by definition, that means V has to be a union of these square boxes, right? But using using our observation, so this is the union of okay, so this I should really use the space better. Okay. Open with respect to this norm. If and only if V is a union of boxes, but box in V this is not by definition, but this is something that we saw. I'm getting a metric. So if I have an open set, then I can put a box centered at each point inside that open set that is totally contained inside that open set. Okay. Now, the point is open with respect to and in the exact same thing, I'm going to get this. So what changes on the right hand side? Instead of a box, I'm going to say diamond. And likewise, open with respect to the usual Euclidean norm, if and only if V is, so X in V, X in V. And what changes here? The only thing that changes is that the shape of so this is going to be a circle in V centered at X, all right? Now, I want you to observe that this is really, all these three conditions are equivalent to each other. Why is that? Can someone articulate this? For example, why is a set V that meets that satisfies the first line also satisfy the second line?
The diamond can be drawn inside the box.
Right. Right. I mean, notice that V is certainly the union of singletons X contained in V. So, but but let's say, okay, so let's say I have a set which meets the first description, that I have a bunch of points and I'm putting a square around each one of them. But then you see inside each one of these squares, I can draw a diamond. And the union of all of these diamonds is still going to be the exact same set. Notice that this is happening for every single point X in the set, right? So this is an easy point, but you have to make sure that you understand this. So what is the upshot? The upshot is that the topology defined with respect to any one of these three norms is the exact same collection of open sets. So let's do this in general. I want to make a definition which captures this phenomenon in general and gives me a way to test this. So the question is, suppose I'm given two norms. Suppose I have two norms and the notation gets a little, a little messy here, because for norms I'm using these double absolute value signs, but I have to have two different norms, so I'm using a prime. R on some vector space, on a vector space C, a vector space. I want to somehow abstract out a property of these boxes and diamonds and whatnot, such that it gives me a way to decide when the topology induced by these two norms is exactly the same. And what was the idea? The idea was that inside each square, I can put a diamond, and inside each diamond, I can put a square. So what this says is that if I take a ball of a certain radius with respect to one norm, then a ball of some radius with respect to the other norm is inside that first ball, and vice versa. So this is one way to formalize the definition, and you see what I'm going to do. We say so. We say that the two norms are equivalent if there are constants alpha, beta greater than 0, such that if I take the norm, if I take first norm, basically each one of the norms lies within a fixed scalar of the other. Such that for all x and b. Okay, so let's stare at this for a little while. All right, so let's, so there are several questions to answer over here. One is, well, why this definition? And you'll see that this definition is good. It will allow us to prove rather easily that the definition of that the topologies that induced by the both norms are the same, and also the notions of convergence with respect to each norm, they are the same. But maybe let's try to first see examples. So example. Let's say that I have the, okay, so let's say I take p equal to infinity and p equal to 1. Are these two norms equivalent in the, according to the definition given? Well, let's check. So, this is just the maximum of all the So can we relate it to this one? Is there any kind of inequality between these? Maybe up to a constant. But there is something obvious, right?
N maximum of mod xi is greater than or equal to.
Right. So the point is that is one way. But this is just obvious, right? Because what am I doing? I'm just adding all the sides. So certainly if I take the sum of a bunch of positive numbers or non-negative numbers, it is going to be at least as big as the largest of them, because the largest one is contributing to that sum. Okay. So this gives me one of those. But notice what is happening over here. I would like to have an inequality where each one of the norms dominates the other up to some constant multiple. So I have some inequality in which the one norm is greater than the infinity norm. So can I have something the other way? Now, the opposite inequality is not true, but you see that in exactly the same way, what I have is that this is certainly greater than or equal to each one of the xi's, right? And therefore, if I just take n times that, then I can say that this is greater than or equal to, just adding the other side, adding.
Okay, sir. So 1 by n serves as the constant.
So good. So that's a good point. So it depends on which one I'm putting in the middle, right? So what I'm putting in the middle over here, before I come to your point, see, this is the one that I'm putting in the middle here. What am I saying? This one is greater than or equal to. So in other words, what is alpha over here?
1.
Alpha is 1 and beta is n. But let's see what his point is that in exactly the, so, or I can say IE. If I want to put this in the middle, if I want to put this in the middle, then what do I get to do? Well, on this side, I'm still going to get the same thing. It just so happens because the constant is 1. But now if I want to say that this is, if I want to put something like this over here, then you see the right-hand side of the inequality that I've written on the previous line, I simply divide both of those, I simply divide both sides of those inequality, of that inequality by n, and I will get this. Yes. All right, so I hope that this is clear. That is, it's very simple. All right, so example. Now, okay, so let's just do the this is the same as saying, if I put the prime norm in between, then what do I get to do? Can I write something so that on both sides I have, on here I have the unprimed norm? Can I do this? Something of this nature? And you see the answer is yes. If I look at this right hand part, this one, yes. And if I divide both sides of this by beta, then you see I get to write something over here. And what do I have to do? Simply divide the norm of x, the unprimed norm of x, by beta, and I will get that. Yeah. In exactly the same way, I get to, so I will just do beta over here. And in exactly the same way, if I divide the left half of the top inequality by alpha, then I will get that. So what this is saying is that, see, a priori, the way I wrote the definition, it's not symmetric in the first norm and the second norm, but it really is the point. Okay? So you see, if I'm declaring two things to be equivalent, then I'm saying that, okay, there is an equivalence relation. It really should be an equivalence relation. So it should be reflexive, symmetric, and transitive. So let's check these one by one. Is it clear that the notion of equivalence is reflexive?
Yes.
Yeah, this is just an exercise in language. You just choose alpha and beta both to be 1. Symmetric is what we just saw over here. And transitivity is something that you can just sit down and check quickly. All right. The respective constants will simply get multiplied. Yeah. So check transitivity. Should we do this? I think really this is something that you can do this on your own. You can do on your own. So check. Indeed, an equivalence relation on norms, on the set of possible norms. Okay, so we saw this example. How about P equal to, so we have three norms, right? So I want to show that P equal to 2 is equivalent to something. Which one will be easier? To check P equal to 2 is equivalent to P equal to infinity or P equal to 1? Just take a moment to see.
I think P equal to infinity.
Yeah, so you see this P equal to infinity is pretty good, no? Because it just picks out the largest one. It's quite easy to handle. So P equal to 2 is equivalent to and P equal to infinity. And now you just look at what's happening. Okay. So let me not write down. Let's look at the first bullet point. Okay. So if on the right hand side over here, if instead of 1, if I'm taking 2, does the same logic hold? Just check what's going on. In that summation, I'm taking squares inside and then taking the square root. Now, inside those squares, I just take only the term that is the largest and make the rest of the terms to be 0. That's what is going to give me this infinity norm, right?
Yes, sir.
So you see the first one goes through in exactly the same manner. How about the second one? The only thing that needs to change, so, is that over here, I don't use this. Instead, what do I do? Because you see, I'm not adding the absolute values of xi's. I'm adding the squares of the absolute values of xi's. So instead of writing that equality, I simply square both sides.
There is it root n instead of n?
Exactly. So just check that. So use same logic to see that it's still going to be this. Of course, if root n works, n will also work. You see, n is 1 or bigger. So, but the reasoning itself gives me this. Let me just check that I didn't make a mistake. Yep. All right. So examples. And should I now check P equal to 1 and P equal to 2?
Not if we prove transitivity.
Right. And just see the transitivity in general, correct? So this I'm going to leave for you to do. Okay. Any questions so far?
Sir, are there norms that are not equivalent to these things?
Right. So this is something that we are going to see later on. We'll come to this question. So the answer is on a finite dimensional vector spaces. On a finite dimensional vector space, all norms are equivalent to each other. On an infinite dimensional vector space, there are inequivalent norms. The first of these we will prove using the notion of compactness. So this is where we are headed. Okay, so currently all this business about norms and them being equivalent has nothing to do with the topology, right? So let's make the connection that what we saw in case of R2 with these three norms, it is really true in general whenever I have equivalent norms. So claim. Okay, so fact. On a finite dimensional vector space. Okay. So what is the point of this definition? Suppose I am given two equivalent norms on a vector space V. Then the notion of convergence and the notion and the topologies with respect to each one of the norms, they are really the same. So let's formulate this carefully. Then xn, a sequence xn converges to point x, v, with respect to this norm, if and only if, okay, so let's with respect to the other norm. And a set open with respect to this norm, if and only if the other norm. Okay, so proof of this. And you see, what we do is we, for open sets, we really just imitate what we did earlier in the picture. Let's do the thing for, let's prove the statement for convergence. Okay. So let us suppose that, remember the two things are equivalent. So I have these constants alpha and beta. Beta times the prime norm. Okay. And this is true for, you know, for any, so this dot is really the same okay, so let's put some, so let's say some y for all y in V. Now, first and simple observation. It says if and only if, but do I have to prove both directions?
No,
No, because you see, whatever proof I see, whatever proof I do, if in the forward direction, I can simply switch the role of the norm and the prime to do the backward direction, right? This is an equivalence relation. So it's a completely symmetric thing. Only one direction is enough to prove for both of the claims. Okay, so let us suppose I'm given an, suppose I'm given, so forward direction, so 1 and forward direction. So,
Hello, sir.
yes.
Sir, by forward direction, you mean you assume it to converge in one of them and prove it to be converging in the other metric too, I mean, in other norm too, right?
Exactly.
Oh,
so let's write this.
Okay.
Let's write this down. Yeah. So suppose I am given that this sequence converges to X with respect to this. Okay. So as I keep repeating ad infinitum, ad nauseum maybe, We write down what is given, we spell it out. We also write down what is required. And very often this will just form the beginning of a path or maybe end of a path, and it will all meet as we just write things down carefully. So what does it mean that the sequence xn converges to x? And what is it that so let's write this down. So given. So what does this mean? For all epsilon greater than 0, there exists there exists capital N such that for all n greater than n, what happens?
Norm of xn minus x is less than
Right, less than epsilon, correct? And what is it that we want? But remember, this is true for all epsilon, correct? This is true for all epsilon. So maybe what we want to do is the following. Let's not use, and what is it that we want?
We can use alpha epsilon.
Right. So that's, so that's the proof in sort of a few words, but I'm just trying to spell it out. So what is it that we want to do? Suppose I'm given an epsilon greater than 0, right? Let's write this down over here in parallel. Want to find n such that, oops. The only thing that is different is that not this, but that. That's what will show that if I'm able to do this for every epsilon, such that for all small n greater than n, this happens. But so, and what is it that I know? So you see, okay, so question. The inequality that I have written here, will the left half of the inequality be useful or the right half? Or will I require both?
Left.
Yeah, so you see, I want to bound the prime norm. I know how to bound the unprimed norm. So what do I know? I know that xn minus x, this is the thing that I want to write less than or equal to something, correct? I want to write that this is less than something. So what is this less than? Well, this is not less than anything, the way it is. It is, but if I want to write it directly, then I know that this alpha times that is less than the unprimed norm of xn minus x. And what is it that I want? So let's see when, yeah. So this is what I know. And I want this left-hand side to be less than see what is given to me. I want this is what I want. But I have alpha times that. That means the quantity that I have, I want this quantity to be less than alpha times epsilon. So you see the proof writes itself out. So let us just change this. I'm going to change this by saying see, this statement is true for all epsilon, right? So which epsilon will I take? I will take alpha times the epsilon that is given as a challenge for the prime norm, for the convergence requirement with respect to the prime norm. So let's write down. Pick n such that, and now let me keep this erased part, and I will change this to alpha epsilon. Alpha epsilon, yes. Do you see that the proof is now done? So this is not written in a linear fashion because I worked my way backwards. So really speaking, what should I do? The sentence, the pick whatever, that sentence should come after whatever I have written. Okay, so let's do it like this. Oops. Let us insert this sentence here. Insert here. And now how do I finish the proof? Actually, no, that's not there. Maybe that's not. Insert here. And so end of the proof. So is it clear? Of course, I could have done this much faster just by saying in the beginning, oh, pick capital N in this fashion. But we went slower, and I actually showed you that this sort of writes itself up if you just keep your wits about and see what is required and make the choice accordingly. Okay. So any questions so far? Okay. So how about number 2? And so converse, so this direction is by symmetry. Okay, so how about number 2? Okay, so let us suppose again that. So suppose, go ahead, please.
Sir, for the second one, we have to just prove it for the open balls, right?
Right. Okay. So we have to, okay. So we can prove it by just for open balls. But let's just explore here. I don't think that going to open balls is going to make our life necessarily easier. So let's just follow our nose and you can see. So what is this? So V is open with respect to that. If and only if. What did we find? What did we say? V is union of balls, correct? V of union of balls. But remember, I can always take the balls in such a way that around each point in V, I'm putting a ball inside V, centered at that point. So this is B R X. So here we can say, so this, okay, so this is ball with respect to but you see, I now just get to do the job. So what did we say over here? That okay, I did not write it down. But okay, so let's see this. So look at, so keep the pictures in mind. So what have I done? V is open with respect to the unprimed norm. And that means that I get to write it as a union of balls centered at each one of the points inside that set. What is the natural thing to do? So this is V over here. And if I'm given a point, I have put a ball over here inside V with respect to one of the points. So what should I do now? In terms of the picture, what should I do? I want to show that V is open with respect to. So this is the conclusion that I want, that V is open with respect to the other norm. But what does it mean for V to be open with respect to a norm? Again, that it's a union of balls, right? So this means in order for this to happen, this needs to happen. X in V and B prime of X of some radius, correct? Remember, this radius R depends on X. So I need to be able to put something over here. And so these are balls with respect to the other norm. So the equivalence written on the first line and the equivalence written on the next two lines, that is just true. Those are independent set statements about the two norms. So is there a way in which I can make this implication work? There's just one small observation required over here. So see if you can find it. We haven't really used the fact so far that both of these norms are equivalent, right? So what would finish the job?
We can take
The scaling of the radius, I mean, you can
Yeah.
scale the radius
That's
according
Right,
to
but how should I scale the radius, right? See, in terms of the picture, what do I want? I have put this ball. This ball is with respect to the unprimed norm. What kind of ball should I find that will do the job, this B prime ball? Something that is contained in this or something that contains this?
contained in this.
Again, say that again, please.
Is contained in.
Something that is contained in here, right? So is there such a ball? Let's go back to the definition. So this is a ball of radius R with respect to, this is a ball of radius R with respect to the unprimed norm. Can I fit a ball of some other radius with respect to the primed norm?
Sir, I think just writing that by taking an element inside the ball
Okay.
with respect to the norm.
Okay, all right. So let's just see. So B R X is the set of all Y such that the distance between Y and X. But remember, the distance just means the norm. So norm of Y minus X is less than R, correct? And B prime of S is the set of all those y such that the norm of y minus x, but the primed norm is less than x, is less than s. What does this tell me? Okay, so unfortunately, I don't have the inequality over here. And we have, okay, so let's just write this down. What I have is that for any v, so for any v, let's not use x because, so for any v, what do I have? This is, so these things together, what do they tell me about balls? Think about it for a moment.
Sir, is it R by beta?
I want to see what the, okay, so let us suppose I have the condition that the middle terms, let us suppose this is given by, so let us suppose the middle term is less than r, right? So v is y by x, so that means that I am taking the ball b centered at x of radius r with respect to one of the norms. Does this contain some ball? B prime. Oh, sorry, this is bad. This is B prime because I'm using the prime now. Does this contain some ball of radius some? Does it?
B R alpha, R alpha radius.
Is that true? Just check. So if I know that the middle term V, if this is less than or equal to R, then alpha times V, alpha times the norm of V prime is less than R. But what does that tell me about the size of, remember, a ball means it's, just think about it for a moment and you will see. Should I put alpha R over here, this subscript, B prime, the subscript that the radius that I have kept blank?
Sir, if a point
R
belongs
by
to
alpha.
It's going to be R by alpha, right? So let's just write this down. It's very simple, but that means I should be able to explain it. So V less than R implies its norm with respect to V prime. So do you see? That means alpha times the norm of V, the prime norm of V is less than R. So the norm of V itself is less than, sorry, what? Yeah.
Sir, if a point belongs to the left ball, then it should belong to the right ball, right?
Yes. Okay. Sorry, you are
So
absolutely right. So what I'm saying is correct, but I'm not applying it correctly. Yes. Okay. So yes, absolutely right. Okay. So now I have confused myself. Let me slowly extricate. Okay, so what this is saying, that if I have something which is in here, then it is also in where? This I think is correct. Yes?
yes, sir.
This is not what I want. So you are absolutely right in pointing that out. So let's write it down the other way. So this is what I wanted, correct? Question mark x, B prime question mark x. So that means I want some inequality on V prime, less than question mark should imply that the norm of V, the unprimed norm of V, is less than R. So what should go in the question? What should go in the place of question mark?
Alpha R.
R by beta.
Yeah. So you see, it's the I want to see the left hand side of the inequality gave me one relation. It told me that some B is contained in some B prime. So it's the other side of the inequality that should give me the other way containment. So this question mark is something that should be in terms of beta. And what is it? If the prime norm of V is
R by beta.
is then yes. Then you see, if I multiply both sides of this inequality by beta, then I get that this one is less than R, and therefore the norm of V, which is bounded by that, will also be less than R. Okay. So the question mark over here should be replaced by B prime 1 by beta R X. So that is what should go up here. R divided by beta. Okay, so maybe it's just schematically I will put it over here. So this one is BRX and this one is B prime X whatever R by beta. Okay, so any questions on this so far?
Hello, sir.
Yes.
Sir, so we are explicitly proving that if a set is open in one of the norms, then it is open in the other one. I mean, for both of these, we are showing it explicitly, right?
Yes. Yes.
Okay,
Yes.
sir. I
Right.
thought you would be using the symmetry.
Well, you see, the reason is because I got confused, right? And so this one is going to be used for the other one, right? That's the one that I got first because
Yes, sir. Yes, sir.
So in the end, we ended up proving both of. Okay, so let's. You're absolutely right. Let's write down the upshot of this. So as a result, I did not. So the forward direction was given by this, but the backward direction is also given by the other containment. Right. Let me not write the backward direction because my picture doesn't corresponds only to the forward direction. And I should say one thing is that if you're lost in here, then please be assured that you are lost only in the notation. There is nothing much that is going on over here. It's just definitions. I mean, which is true for all of mathematics, that it's just definitions and reasoning based on that. But here the reasoning is very, very little distance away from definitions. The only thing that is extra here is this small technical result that we keep using again and again. That inside any open set, you can take any point and put a ball centered at that point contained in the open set. That's what we keep using again and again. And where does that come from really? It just comes from triangle inequality, nothing else. Okay, very well. Okay, so where are we? So we've good. So we've done and so what is the corollary of this? So corollary. All P norms on Rn and Cn give the same topology. Okay, maybe we should not, because I haven't really done it for p equal to 1 and p equal to infinity norms give the same topology as p equal to 2. The reason why I separated out the p equal to 2 norm is because when we usually say ball, perhaps we mean the circle or some sphere in n dimensions. We saw earlier that this p equal to infinity norm is really nice. It makes things, you can do things easily with respect to that. So let's see one other sort of application of this. So another corollary. Here I have to be a bit careful about notation. So let xm, and just for let me just say x. See, what I'm going to do is the following: be a sequence in Rn. So now I'm taking a sequence in Rn. That means that each one of the elements of the sequence is a point in Rn, and it's going to be a tuple. And I'm also going to be looking at the coordinates of this tuple. So there is going to be double indexing. I want to avoid double subscript. So okay, so let's do the following. Let's put a bar on this, okay, to show that it is a vector, like we do in school. Let's put a notation. xm bar is xm1 up to xm n. So I'm going to put superscripts over here. So the question is, what does it mean for such a what does it mean for a sequence of vectors to converge to a vector? And the thing is, we want to say that it really is the same thing as it's going to be a pointwise convergence. How do I check that? So just see what's happening in the first slot, ignore all the other slots. Then xm bar converges to x bar, which by notation is going to be just x upper 1 up to x upper n. With respect to, let's say, this norm. But really, it could be any norm, right? If and only if I get this slotwise, xmi converges to xi in R for each I. Okay, so this was a bit of a mouthful because I also introduced notation. Is the meaning clear? To check that a tuple of a tuple of numbers in Rn, a sequence of tuples of numbers in a sequence of points in Rn converges to a point in Rn if and only you just see what happens slot-wise. You can say what is there to check in this, right? But notice that the notion of convergence on Rn depends on the distance that I have put in Rn. And I could be taking the Euclidean metric. Then it is not so obvious. However, this is going to be very easy because proof with respect to any norm that I like. that is equivalent to the Euclidean norm. So that which will be all P norms. But what we have proved is certainly the 3 norms, right? So let's just check this. So what works? Because we saw that the notions of convergence are the same. So what does it mean that xm bar converges to x bar with respect to this norm? What does that mean? What does it mean?
So the maximum of the tuples differ by epsilon after a given n.
Correct. So let's write this down carefully. For all epsilon greater than 0, there exists n such that for all, and now I don't want to take small mn because following Pramath, I have used m as the general element. What happens? Now here is the thing. The norm has to be bounded by epsilon. But what is the norm? The norm here is the infinity norm of the difference between x bar and xm bar. But what is that? That is just the maximum of the first coordinate of xm minus the first coordinate of x, and all the way up to the last coordinate of xm minus the last coordinate of x. So this is less than epsilon, right? But that's really saying exactly the same thing as all this, etc. What does it mean that the maximum of a bunch of numbers is less than epsilon? It really, not only does it imply, it really is equivalent to saying that each one of those numbers is less than epsilon. So each xmi minus xi is less than epsilon for all I. But that's really exactly the same thing as saying that limit as m approaches infinity of just these real numbers is equal to x sub I. So you see that it is really convenient to use this infinity norm, right? Okay. So how are we on time? We just have a little bit of time left. Okay, so let me just say, so with this in mind, so let me just open the exercises from last time. Yeah, so last time I asked you to show that, so exercise from last time. About continuity. So do these exercises. In particular, what I said is, when is a function from a metric space into Rn continuous? Because such a function will just consist of component functions, right? Made up of component functions. So maybe this exercise is helpful to you. I mean, the corollary that we did is helpful to you. Just think about it. Okay. Since we have like maybe just a minute or two, let us go ahead and sort of start the next thing. At least let's introduce the words. So compactness, and so the word compact was not defined last semester, but we will do that maybe just as the first thing. What property of the closed interval did you prove? What key property of the closed interval did you prove last time? Something
That
about
the extremums of the function are contained within.
right. Yes. Okay. So that is for a function that is defined on a closed interval, a continuous function defined on a closed interval.
Yes, sir, the supremum of the interval will be contained in the interval.
Right. But in particular, supremum is also just a number. It cannot be an infinite.
I think you are talking about Bolzano stress.
Right. So, but okay. So what I want to say is that what about a sequence of numbers taken from a closed interval? Anything? Do you recall anything? If I have a sequence of numbers,
Its limit will also be in the closed interval.
well, this sequence may not have a limit.
So it
I mean,
has a
yes.
convergent subsequence.
Right.
Yeah, if it's bounded.
Right. But you see, the point is, okay, so bounded, all right. So you did it like that. But you see, if I have a closed interval, then every sequence in this is going to be bounded, no? So it will have a convergent subsequence. This notion, somehow a sequential notion, we want to notice one thing. We have sequence. So there was a notion of continuity using sequences, but we have reformulated it using topology. So we want to have something called compactness, which will be defined purely in terms of topology. This definition is a little hard to motivate, but it has proved enormously useful. It was not the very first notion that that came up when people tried to abstract this idea of what is it so that is so great about the closed interval. So it took some time to get to the definition of compactness. Let me just say that, read the definition. And we will take up the theme from here. We will take up this theme on Monday as the very first thing. This will also help us prove the statement that we made earlier, that all norms on a finite dimensional vector space are equivalent. So please try to read this, and also please do the exercises that were assigned in class, because the first homework is coming shortly and it will be taken up largely from, it will consist of exercises that are largely taken from what I have assigned in class. So with this, let's stop for today.
Recording stopped.
Any questions? I mean, if there is anything, by the way, so yesterday in my office hours, I had to leave early. So I think one or two of you may have tried to contact me, but I will be available later in the day today. So if you want to discuss something, just give me a call. I also have an unfinished discussion with one of you. So just feel free to give me a call later in the day today after 5 o'clock. Okay, so there is a question. So do P norms of real numbers exist? I'm not really sure what that question means, because we did define what it means to be a P norm, right? There was a definition. Yeah, so this definition you see in the middle of the page, P norm. Now, I have claimed that it is a norm for every single value of P between 1 all the way up to infinity, but we have proved it only for 3 values. So we have not proved it, but it is a norm, which we will prove at some point. I'm not sure if I understand the question. If not, please clarify. Are norm root 2 and norm infinity equivalent? So in other words, I understand what you're saying is that norm root 2, by that you mean when p is equal to square root of 2. What that means is that you're adding square roots of norms of individual components and then taking the square of the whole thing. Okay? Perfectly valid. Square root of 2 is bigger than 1. So this is a perfectly valid norm. And the answer is yes. This is a norm, and all possible norms on a finite dimensional vector space are equivalent. We will see this as a result of Heine-Borel, as a consequence, essentially a consequence of that. Okay, anything else? Was the term open cover mentioned last semester? You know, cover of real numbers or cover of an interval?
I don't believe so, sir.
Okay. All right.
It's
Fine.
just open set containing that, right?
Yeah, open cover of a set just is a collection of open sets whose union contains that set.
Yeah. This is
So,
essentially the
all right.
open
So
cover type
okay. So let's just explore this. So compactness says that if compactness of a set is defined to be the following: that any open cover of the set contains a finite subcover. Is the closed interval compact? I mean, the answer is yes. The closed interval is compact. So can we prove this? It will take some work to.
Any open cover of open closed set will be just like for R it would be if a closed A comma within A plus K, A minus K and B plus K of the form.
Yes, that is true.
That is essentially a finite cover.
No, but okay. So I think, okay, so I should really say what a cover is. A cover means a collection of open sets such that the union of those open sets contains the given set. So you see, when I'm covering an open, let's say closed interval from 0 to 1,000,000, I could be covering it by open sets of width epsilon. Epsilon could be very tiny, small open intervals.
Yes.
But nonetheless, it's going to be so okay. So why should any open cover of a closed interval have a finite subcover?
Open cover has finite length.
No, what does it mean length?
Okay, the closure like
you see these open sets that you could be taking. maybe open intervals. You see, by the way, a general open set of real line is not an open interval. It's just union of those. And they could be spread out in some way. You don't know. But okay, anyways, let us suppose that instead of taking you might as well take every open set to be a ball, because you see, I'm taking their union. So if a union of, so let's say let's fix some notation, fix some names. So let us say my set is S, and now have some open sets V alpha such that union of V alpha contains S. And I claim that, not claim, the definition is that S is called compact if I can always pick a finite number of this family such that the union of these finitely many sets itself covers S. It does not matter how I chop up my open sets into tiny bits. No matter what open cover I take, I will always get a finite subcover. That's the definition of compactness. Okay. So I want to show that the closed interval is compact. Any closed interval is compact. Okay. So maybe first thing, is an open interval compact? Suppose I take open interval 0, 1. Is it compact? I claim it is not. Can you show me?
Take like 1/2 power n type sequence.
Right. So for example, you can do the following. Take the following open cover. Okay, let us say 1/3 to 1, then 1/4 to half. You see what I'm doing, and keep on going like this. I cannot really take half to 1, then 1/3 to 1/2, because I will miss those points. You see, I want to cover the whole thing. So I have to take slight overlaps in between. So let's say take all intervals of the type 1 over 2 consecutive odd numbers and 1 over 2 consecutive even numbers. Those types of intervals. So all things of the type 1/3 to 1, 1/5 to 1/3, 1/7 to 1/5, and so on. And then also half to quarter to half, 1/6 to 1 to quarter, 1/8 to 1/6, and so on. Just check. I mean, what's happening over there is neither here nor there. But you see, the point is all of these sets, they're accumulating towards 0. But 0 is not part of the interval, right? So you see this infinite cover. Do you notice that it will not have any finite subcover? Because if I stop anywhere, there is going to be a smallest point. If I take only a finite number of them, then among all the endpoints that I'm taking, there is going to be a smallest positive number, and there is a whole ocean between that and 0. I mean, it's very small, but in terms of the cover that I have chosen, I can never do it with finite number. On the other hand, if I include the number 0, then 0 will have to be covered by one of the open sets, and you see that will capture. So you begin to understand what's going on. Somehow this. So see if you can prove this.
Hello, sir.
Yeah.
Sir, for being compact, every open cover has to have a finite subcover.
Yes, that's precisely the definition. Exactly what you said.
Okay, okay.
Not there exists a finite cover, which is kind of silly, because then you can just take the entire space. So every open cover has a finite subcover. Why this definition? It's a little hard to motivate, but we just take it for now.
Sir, will we spend some time motivating it? Because I've been thinking about how to motivate it, and all. I'm not I see that it is a nice definition, but I would like to see the motivation also, because I so far have not been able to think of a very nice one.
Well, I have some kind of answer to that, but I don't really have a very good answer. I think I have to look around to see. But you see, this definition, it took a while. You can look up the history of the definition of compactness. It took a while. So there was the sequential notion of compactness, which I think is that every sequence in that set has a convergent subsequence.
Yes, sir.
People did that for a while. And you see, for many kinds of spaces that we consider, the two definitions work out to be equivalent. I think it's true for metric spaces, certainly, that.
Yes, sir. I think it is.
So, and you can say, well, many of the spaces that we want to consider in life are metric spaces. So why bother? But there are other kinds of topologies also. You see, the more general point, which I forgot to make today in the lecture, is that last time I said, okay, how much of the stuff that we are doing, last time we did closures, but more importantly, continuity. And some characterizations could be stated purely in terms of the topology. But then there were things where we use the notion of size. And there were formulations that used sequences. So forget the size part. But a sequence certainly makes sense in any topological space. So to what extent can we make definitions with sequences and characterize continuity, etc. in terms of this? And the answer is sequences don't really work all that well in general. So this convergent subsequence, that's also using the subsequence definition, correct? Now, by the way, we should really say, what does it mean that a sequence xn converges to x in a topological space? There is no epsilon or delta. So what does it mean that xn converges to?
So we can always get some open set for every neighborhood of that. If xn converges to x, then for every neighborhood of x, there will be capital N such that n greater than equal to n, all the xn's will be contained in that neighborhood.
Right, exactly.
And neighborhood, I mean,
okay.
open sets.
So basically, you are replacing that epsilon interval by an arbitrary neighborhood, an arbitrary open set, right? This can lead to some funny things. So just a dumb example. Let us suppose I take a topology, which is the topology that consists of the entire space and the empty set. So I take this topology on R. The only open sets are R and the empty set. Now take a sequence. What does it mean to have a limit of this sequence?
So could you repeat the topology one more time?
Yeah, the topology on R is the empty set and the entire set of real numbers. Those are the only open sets. And let's take a sequence, all right? Let's take the sequence 1, 2, 3, 4, so on. Does this sequence have a limit? Think carefully. Now I claim that minus 27 is the limit of this sequence.
Okay, so with this definition, the limit need not be unique.
Yeah, so you see every
point is a limit.
Every point in R is a limit of every sequence in R.
Yeah.
Right? So you see, the definition is a reasonable attempt, but it can be very badly behaved. Right?
So, what was the definition again?
The definition of xn and a sequence xn converges to a point x if every neighborhood of x contains all but finitely many points of the sequence.
Okay.
So you see, if your topology is coarse, if your open sets are not small, then this is going to be a badly behaved definition. Limits need not even be unique.
Right. I guess this definition doesn't enforce any kind of smallness.
Right.
On the neighborhoods.
So you can take various kinds of things. You can say, okay, some notion, maybe it may be interesting. But one way in which one sort of take that people have on this is that, look, if you want to use things, sequences are not really good enough. Because what is a sequence? A sequence is a function from natural numbers to your space. And natural numbers are ordered. So if you want to have something similar, then people generalize sequences and they define something called nets, which is a function from a directed set. So instead of natural numbers, you use some other kind of indexing set, which still has some order structure on it. And
That is still countable, right?
Not necessarily. Not necessarily. And if you use nets, then many of the theorems which fail, that is, some topological properties can be formulated in terms of sequences. Right? We have seen this for continuity, then we will see this for compactness. So those things fail for general kinds of topological spaces. It may be true for metric spaces, but it fails for general kind of topological spaces. So one way to repair this is to generalize what we mean by a sequence. And there are some ways to do that. There's something called nets, but it is very far away from our brief in this course. I mean, our brief in this course is not topology. Topology is a soft subject, whereas analysis is more rigid. I'm not more rigid, but it's more quantitative. Analysis is about estimates and things like that. Topology is about open and closed sets. So can apply to many more situations. So, I mean, these kinds of...
Is there any concept of that, instead of taking the finite union, we allow countable union or LF1 union or LF2?
Right. So I don't know the answer to that question. I'm sure it is inconceivable that this has not been thought about, but I don't know the answer to that question. If there are, if there are interesting things to be, if there is an interesting definition to be made. I presume you are saying that instead of a topological space, you are saying, okay, some other kind of thing where we use more general unions.
No, I was saying about the compact definition. Like instead of taking a finite subcover, if we allow that countable subcover or LF1 number of subcover.
Not sure.
In bigger sets.
But you see, here, I don't see, for real numbers, this really would not make much sense, because
countable should make sense.
I mean, you see, makes sense in that you can make a definition, but do you really want your open interval 0, 1 to be compact?
It might be called compact star or something. Yes.
But you see, I mean, we have some, okay. So the point is, why do we want compactness? Because we get to do some things with it. If there is a finite thing, then you get to add, so there are like functions with compact support or something like that. So if you have finite things, I can add finitely many things. I cannot add infinitely many things without convergence. So things like, so you see, compactness is, we define compactness because it is a very useful tool to do things. So if you make a definition, then it's perfectly fine. Everybody has right to make whatever definitions they want, but why is it interesting? What applications does it have? I mean, I don't know, but I mean, such questions would be asked. What interesting properties can you prove about it, and where can you use it? I mean, the point is, this Borel, it says that compactness is going to be characterized in our spaces, non-linear spaces, finite dimensional non-linear spaces. That will be, those are exactly closed and bounded sets. And that is a big deal, because technically it is a very useful thing. Okay, so spaces admitting countable subcovers are called Lindelof spaces. Okay, very good. So where do they come up? I presume it means that every open cover has a countable subcover. Is that it? So this is what Ayan has said.
Yes.
Okay. So I don't know where they come up. There is another notion of compactness, where you see real numbers are not compact, or Rn is not compact, but it's a very nice space. So there is something called paracompactness. But we really want to sort of get done with topology as quickly as possible. And I dawdled in the beginning. So we are not late, because we are taking 3 hours, three classes a week. But we really do need to get a move on. See compactness, prove Borel, and go to define derivatives. That's when sort of the course proper analysis part will start. For us, topology is really in the service of metric spaces, which themselves are in service of non-linear spaces. Okay, good. So if there is nothing else to discuss, then we will stop, and we will continue on Monday. You should also expect the homework shortly. So please do the problems that have been assigned in class. That way, when it comes, it will be very quick for you to just finish it off. Okay, good. So bye, everyone. We'll see you on Monday.
Thank you, sir.
Thank you, sir.